Good morning, students. The first time I recorded this, the sound for whatever reason did not work, so I'm recording it again. If you've already watched this, I can see on Edpuzzle that you have. You don't need to watch it again unless you want to just watch it so you can actually hear my explanations and understand it a little bit better. So we're going over substances and mixtures. There's a difference between the two, and you want to understand that. That's the main point of this set of notes here. So a substance is a homogeneous thing. What does that mean? It means that it's uniform throughout. So if I take a sample of the substance over here in this sample, I can find the same thing in any other part of the sample. For example, if I have water, pure water, with nothing else, if I have a cup of that, at the top of the cup I'll have water, in the middle of the cup I'll have water, at the bottom of the cup I'll have water. We call that homogeneous, same throughout. It also has a definite composition, meaning that we have a particular chemical formula for water, and that does not change. The last thing is that it is not physically separable. Certainly we can separate water, but physically we can't do that with like a sieve or something. We have to add electricity or a lot of energy in order to break the chemical bonds between hydrogen and oxygen. So examples of these are an element, right, or a compound. I talked about water as an example, but you could also have hydrogen. Hydrogen is an element. It can be hydrogen gas, H2. So either one of those can be substances. A mixture, on the other hand, is something slightly different. So a mixture is two or more physically separable components combined in one space. So it's two or more physically separable substances combined in one space. Okay, now we have two different types of mixtures. We have a homogeneous mixture and a heterogeneous mixture. A homogeneous mixture is called a solution. And whenever you dissolved sugar in tea, right, whether you've dissolved salt in water, you've noticed that it dissolves and that the taste of the tea, for example, is uniform throughout if you've mixed it well. Again, what that means is that it's homogeneous, that it's the same throughout, same composition throughout. So a solution has particles that are very small and they've dissolved in each other. Typically, we're talking about a polar molecule like sugar or some sort of salt where the water dissolves it because water is also polar. You'll learn in a later video that like dissolves like. So polar things dissolve polar things, non-polar things dissolve non-polar things. Also, if we shine a light through it, if you take a flashlight and you shine it through a glass of sugar water, you'll see that the light goes right through. It doesn't actually hit any of the particles in the mixture, the homogeneous mixture. And what that looks like is you'll see the light of beam going towards the glass. You won't see any light in the actual glass, and then you see the light coming out of it. Again, that means that it's not hitting any large particles enough to make it scatter and that you can see the beam in the cup itself. Now, this is different than a colloid in suspension. In colloids, particles are not as big as suspensions, but are larger than solutions. So particles, oops, are larger than solution, but smaller than suspension. An example of this is a glass of milk, particularly if the milk is very watered down. And what this does is it shows the Tyndall effect. This is where light is scattered by the particles in the actual colloid. And we'll take a look here. Okay, so in this video, as you can see, as it's starting to start up, oh my goodness. Sorry for the technical difficulties here.
Every morning, we can see sunlight shooting through the window. This natural phenomenon is due to scientific theory known as Tyndall effect. But what is Tyndall effect?
So, again, we see the Tyndall effect not just in a glass of milk, right? Why do we care about the Tyndall effect? Well, because we see it all around us. We want to understand what's happening. As you can see, the beam of light is being scattered by the particles in the air in this case. That's why you see the beams of light here. All right, so like a dusty room, for example, when light comes through, you can see the dust particles. You know that they're large enough to be a sort of colloid in the air because you see the beam of light. All right, so basically, when we put like milk in water, for example, this is what we see. We see the beam of light going through the cup. If you wanted to do something like this, you can also, create this where you have a bit of milk in one and a bit of water in another. As you can see here with a laser beam, this is water here. This is obviously not a colloid. It's not showing the Tyndall effect. Why? Because I can't see the beam of light in the water on the right-hand side. The left-hand side bottle has a bit of milk in it. And you can see that it's showing the Tyndall effect because I can see the beam of light going through. And the reason why is because the light is coming through and it's scattering these light particles when it hits the colloid. And as a result, you can see the beam. There are several pieces of technology that use this principle. One is a turbidity meter, which is great for measuring things like wastewater. When you're at a wastewater treatment facility, you have to make sure that the turbidity is low enough before you pump it back into a river that's next to it. And you have to check the turbidity, which is a checking of the amount of Tyndall effect or murkiness that the water has. And also a smoke detector. Smoke detector also determines how how thick the particles are in the air, and the thickness of the particles will determine whether or not the smoke detector should be, sounding the alarm for a fire. Going back to our notes here for a second, the last part is a suspension. So, as you probably guessed, a suspension is where we have the largest particle. So let's put a little divider here. Particles are large. You can imagine that when particles get so large, they don't show the Tyndall effect because the light doesn't pass through it, right? So imagine like dirt in water. Eventually, there's so much murkiness that it doesn't show the Tyndall effect. Okay, you can't see the scattering of light. And usually with that, you also have a settling that can happen where if you leave that suspension alone, you'll start to see different layers filtering out physically without you having to physically like strain it. An example is like muddy water. It says muddy water there. All right, so the last part is whether or not you can fill in the chart below. I want you to pause here and I want you to see if you can fill in the chart below, right, with all the words. On your sheet, you should have blanks and descriptions below those boxes. All right, see if you can do it before I move on. All right, go ahead, unpause. Let's see how we did. So matter is split up into two categories. One is homogeneous or homogeneous. The other one is, and it's also definite composition. The other one is two or more physically separable components. So this would be a substance. This would be a mixture. In terms of substance, we have one type of atom, which would be an element, or two or more types of atoms chemically bonded, that would be a compound. We have two different types of mixtures, right? We have homogeneous and heterogeneous. Homogeneous means uniform properties, and heterogeneous means varied properties throughout. With homogeneous, we have the example of the solution. We have something dissolved in the water, and we now know what, if you look at the next video, we now know what the dissolving process looks like, so check back with that afterwards. And then you have another type, which is showing the Tyndall effect. This would be a colloid. And last one is a suspension with the largest particles. Okay, and that's it for substances and mixtures.